So Rutherford's experiments and the experiments of other scientists after the discovery of the neutron, we come up with this picture of the structure of an atom, that it's made up of electrons, protons, and neutrons. The protons and the neutrons being together in a very dense nucleus, and then a lot of empty space around this nucleus. Some of it is the electrons whizzing around outside. So the electrons have a -1 charge and the protons have a +1 charge. This is just a relationship to physics if you are interested. Then we have the mass. The electron has hardly any mass compared to the proton and the neutron. It does have some, but it's much, much smaller. When we write an element in a way that shows all of these particles, this is the symbolism that we use. E is the elemental symbol. So the periodic table has either a single capital letter or a capital and a lowercase letter to represent each of the different elements. If we want to write the number of protons that are in that element, it's kind of redundant, but we can write it. We would write it as a subscript to the left. So for instance, carbon has 6 protons. If we don't write that 6, we still know that carbon has 6 protons. It always has 6 protons. If there's some element that does not have 6 protons, it's not carbon, but we can write it anyway. Then the mass number of a particular atom is the sum of the number of protons and neutrons. So not all atoms of carbon have the same number of neutrons. They all have the same number of protons, but a very common scenario is to find a carbon atom that has 6 neutrons and 6 protons, making a total mass of 12. If you wanted to represent this, you could also do this because a carbon with 12 mass units has 6 protons. You would know that as well. So it could be written either way. This 6 is a little extra information. We're going to say that this carbon atom does not have a charge. If it did have a charge, we would write it in an upper right-hand corner. So it would be where this asterisk is as a superscript to the right. If it's 0, we don't have to write it. So this is the way that we represent the particles that are in a particular atom. Let's see if we can go the other way and look at one of these symbols and tell what particles are in there. All right, I'll just point out these here that weren't quite fitting on the screen. This is 2 different magnesium atoms. They have the same number of protons because they have to, but they have slightly different masses, and that's because they have a different number of neutrons. And we can call these 2 magnesium atoms isotopes of each other. And then these are just different ways that you can express the isotope. If you don't want to write out the whole thing, again, you don't have to put the 12 because that's extra information. And so a lot of times they will just specify that this is magnesium 25, written this way or this way. Let's take a look at these review questions over here. A particle that has charge but hardly any mass would be the electron. The proton also has charge, but it does have mass. So the proton and the electron have charge. The proton and the neutron have significant mass. All right, let's see how we're going to figure out for this table the number of protons, neutrons, and electrons in these isotopes. So written like this, the subscript to the left would be the number of protons. So that is pretty easy to figure out. The mass number is the sum of the protons and neutrons. So if we take the mass number and subtract the protons, we will end up with the neutrons. So we're just subtracting protons from both sides of this equation. To find the neutrons, we can just do this. All right, so this asterisk here, this star, is the charge. If something has a charge, it would be the protons minus the electrons. The protons are positively charged, so those add to the charge. Electrons are negative, they get subtracted from the charge. So then if we add electrons to both sides of this equation, we get the charge plus the number of electrons equals the number of protons. And then if we subtract the charge from both sides of this equation, we get that the electrons are the number of protons minus the charge. So that's a way that we can figure out the electrons. So now we have a way to figure out the protons, the neutrons, and the electrons. The first row is done for us, but let's make sure that this plan works for that. So the proton is this number here, the subscript over to the left, so that is pretty easy. Neutrons, to find the neutrons, we're going to take the mass number, which is the superscript to the left, and we're going to subtract the number of protons. 17 minus 8 does give us 9, so that is how we found the neutrons. And the electrons is the number of protons minus the charge. So the number of protons is 8. If we subtract the charge of a -2, we do get 10. So that is how we found the number of electrons. So the protons here are just the subscript to the left, 6 for carbon, 26 for iron, and 17 for chlorine. For the neutrons, we're going to take the mass number and subtract the protons. For this one, we get 8. For this one, we get 30. And for this one, we get 20. For the electrons, we're going to take the number of protons and subtract the charge. This carbon has a 0 charge, so it has 6 electrons. The 6 electrons and the 6 protons balance out to give a 0 charge, so that's a good double check. Just like this one, if you have 10 negative charges, 8 positive charges, you're going to have a total overall charge of -2. So here, if we have 26 protons and we subtract the +2 charge, we find that we only have 24 electrons. 24 negatives and 26 positives add up to a +2. And for the chlorine, we take the 17 protons, subtract the -1 charge, and we get 18 electrons. 18 negative charges and 17 positive charges add up to -1. So here we know the protons, neutrons, and electrons. We're going to try to figure out what we have here. So the protons would be the atomic number 11. The mass number would be the protons and the neutrons added together. So 11 plus 12 is 23. So this would have a mass number of 23. We can look on the periodic table, and the element with atomic number 11 is sodium. So we could figure out the elemental symbol that way. And then the charge is the protons, the +11, and then -10 for the -10 charge coming from the electrons. So altogether that is a +1 charge. If you wanted to calculate what the average score on, let's say, a class assignment was, maybe the normal way you would think about doing that would be to take each score and add them all up and then divide by the number of scores that you have. But if you didn't have each individual score and you only knew that 40% of the class had gotten 1 score and 20% of the class had gotten another score and 40% of the class had gotten a 3rd score, you could still do that calculation and calculate the average. So what you can do is take the abundance of the score and the score, multiply them together, and then keep adding those. Let's try that with an example. So we're going to calculate the average atomic mass of iron, but we cannot possibly add up every single atom of iron in the world and add those all up and divide it. That's not possible. We're going to have to use these abundances. So we have 91.75% of iron being iron 56. So when we do this, instead of using 91.75%, we're going to use the actual fraction. Because if we multiply this by 91, we're going to get a mass that's almost 100 times too big. So what we need to do is take the fractional abundance, so 0.9175 times the mass, which is 55.9349 AMU, and that gives us 51.32022705 AMU. I wrote these digits smaller because this result only has 4 significant digits, because that's all we knew the percent, to 4 significant digits. Then we'll take the next isotope, iron 54, and multiply the mass times the fractional abundance. So not the percent, we're going to use the fraction, 0.0585. And that gives us 3.1554666 AMU. And this one only has 3 significant digits because that's all we have in that percent. And then with the next isotope, iron 57, it's 2.12%, or the fraction 0.0212 times that mass. And this result also has 3 significant digits. And the last isotope, iron 58, has just a very small fractional abundance, only 2 significant digits, so we just have a very small number here for that result. So once we've done this, multiplied the fractional abundance times the mass for each of these isotopes, we are going to add them all together. That's what this summation sign means. So that gives us 55.8449810.7 AMU. And all of these happen to go 2 places past the decimal, so when we add these up, we can keep 2 places back past the decimal. And so our average atomic mass is 55.84 AMU. And this makes sense because most of our iron has this mass, and so we're going to end up with an average that's really close to that number. So make sure that your answer makes sense. It's really easy with a lot of these digits to get the decimal point misplaced, and so if you make a calculation error, you will probably end up with an average that makes no sense at all. So since most of these are close to in the 50s, getting an answer that's in the 50s makes sense. We can go the other way also. So if you know what the average is, if you know the average atomic mass, and you know that there are only 2 isotopes, we'll call them X and Y. So we have the fractional abundance of the first isotope X, so we would multiply that fractional abundance times that first mass, and then we could multiply the fractional abundance of the second isotope times the second isotopic mass. So this is how we would calculate the average atomic mass. If we know the atomic mass and the isotopic masses, the masses of each isotope, and what we don't know is X and Y, we can solve for X and Y because we know that X and Y add up to 1. So we can substitute the Y with 1 minus X, and we'll have just X in the equation that we'll be able to solve for. Okay, so here we have our problem that we have an element that has 2 isotopes. We know each of the masses of those isotopes, and we know the average. So we have enough information to figure out what the fractional abundance of each of those isotopes is. And then the question does ask us to report it as a percent. So we'll report it as a percent when we're done. So if we did not know the average atomic mass, what we would do is take the fractional abundance of rhenium-185 and multiply it by the mass of rhenium-185. And then we would take the fractional abundance of rhenium-187, multiply it by the mass of rhenium-187, and then we'd add both of those numbers together. In this case, what we don't know is X and Y. We do know the other 3 items. And we also know that X and Y add up to 1, and that Y is therefore 1 minus X. So we can replace the Y with 1 minus X, and then we'll only have X in the equation. So here's what that looks like. This is our average atomic mass. This is the mass of rhenium-185, and this is the mass of rhenium-187. So then it's just a bunch of algebra manipulation to figure out what X is. So I rewrote this one with the X after the number because that just seems more normal. And then I distributed the 1 minus X times this 186.9558 AMU. So I have 1 times 186.9558 AMU, and then I have a negative X times 186.9558 AMU. I'm going to go ahead and subtract 186.9558 AMU from both sides of this equation. So that gives me negative 0.07488 AMU on this side. We only know this 3 past the decimal, so I tried to write this fourth position as a subscript, just to keep in mind that we have 3 significant digits now. And then when I take this away, I'm just left with these 2 terms on this side. I'm going to go ahead and combine them now. When I subtract 186.9558 from 184.9530, I'm left with negative 2.0028 AMU times X. And now to get X alone, what we have to do is divide both sides by negative 2.0028 AMU. So here's what that looks like. Negative 0.7488 divided by negative 2.0028 gives 0.374 as X. The AMUs cancel. This is just a fraction. And it can also be expressed as a percent. So this is 37.4%. The abundance of rhenium-185 is 37.4%. So 37.4%. Okay, so now we need Y. Y is 1 minus X, which is 1 minus 0.374, which is 0.626. So our fractional abundance of rhenium-187 is 0.626. Our percent abundance is 62.6%. So this is how we would figure out the percent abundance or the fractional abundance of the 2 isotopes. Let's take a look at some of the resources we have on Canvas to help understand the average atomic mass and isotopes. If we click on the Fun with Isotopes page, we have some links to different resources. There is a page where you can build an atom, so if you need to understand more about protons, neutrons, and electrons. I wanted to take a look at the atomic mass webpage. We'll go ahead and start that interactive simulation. So if you want to see how the number of neutrons affects a certain isotope, you can work with some of the smaller elements in the periodic table. You can add a neutron and see how it changes the mass number of the hydrogen. It tells you how abundant this isotope is in nature, so that's kind of interesting. If instead of isotopes you click the mixtures page, you can take a look at how the average atomic mass is affected by the combination of isotopes that you put into your mix. So you can use these buckets, or it might be faster to use dials. So if we have a bunch of magnesium-25 in there, if it's 100% magnesium-25, then the mass is going to be really close to 25. It ends up being 24.98584. So it doesn't end up being exactly 25 because the mass of the proton and the neutron are not exactly 1. Or if you have a mixture of magnesium-24 and magnesium-25, that's going to lower the average. The average is no longer going to be close to 25, it's going to be somewhere in between 24 and 25. So let's make it 50% magnesium-24 and 50% magnesium-25. So now we have a 50-50 mix, and we're just about halfway in between the mass of magnesium-24 and the mass of magnesium-25. So you can make different mixes, or you can see how the mix in nature actually exists. So in nature, it's mostly magnesium-24 with a little bit of magnesium-25 and a little bit of magnesium-26. And that is what makes the average atomic mass close to 24.3. So I would encourage you to play around with this if it helps you visualize and understand what we're talking about with average atomic mass. Another interesting resource is the periodic table that shows all the different elements and what mixtures are found in nature. So we have some elements that are almost all one isotope or all one isotope. We have elements that, like magnesium that we just looked at, that are mixtures of 2 or 3 different isotopes. We have some that are a mixture of quite a few different isotopes. You can zero in on any one isotope to see what the mass of that isotope is and what the percentage is in nature. So here we have this one. You can even hover over it to see that information. So you can see in nature the different mixtures that exist. And that is where I got the information for the problem on iron in the note packet. So knowing the mass of a certain isotope and the percentage of the certain isotope, we can calculate what the average atomic mass would be.